Hi, my name is Andrew Wills. I'm from UCL in London, and I'm going to be introducing you to the application of representation analysis to magnetic structures, particularly in crystalline solids. So these are ones where we have translational symmetry. So when we talk about group theory, the first thing to understand is it provides you a framework that we can use to help us simplify the analysis of problems, but we can also use it in conjunction with other frameworks, such as that of energy, free energy, and Landau theory. When we start putting these things together, we start making a set of rules for what's allowed, for what's not allowed. And we can start thinking about what's allowed if and only under particular circumstances. We can think about couplings. We can think about relating symmetry to physical properties. So it comes as a framework that allows us to put different things together. Now, history has given us several different formalisms for symmetry when we're dealing with magnetic structures. We have space groups, black and white space groups, colored space groups, spin space groups, zip space groups, lots of different types of space groups. Then we have representation theory. Now, this is often interpreted as being the method of Bertaut, but the method of Bertaut isn't all of representation theory. It's particular techniques within representation theory. And there's a broader theory framework that I'd like to be talking about. In general, which is best? Well, the two techniques are different. It's like the early days of space groups where we have Fedorov and Schoenflies coming from different directions. Space groups, magnetic space groups and representation theory highlight different things, and people prefer to use whatever they think is most appropriate. In general, symmetry is a language. Now it can there are different views of this language. You start off with a group, but in general, the term symmetry is a non-specific term. I prefer to think about a hierarchical structure with different types of symmetries between different frameworks relating to different focus points of the different structures. When you have these structures, you can also start thinking about what's unseen, why your refinement is only part of what is happening. So I'd like you to start thinking about how to translate what you do and your problem into the different types of languages. In terms of basics, we need to go through why we invoke symmetry, multiplication tables, basic group theory. We need to go from point groups to space groups and crystalline solids that have translational periodicity. And this makes things a little bit more complicated, but we can still work through the same types of mechanisms. We need to go to irreducible representations, or then we need to go further to basis functions. We need to start off with the Brillouin zone and the propagation vector, work through the space groups, and start thinking about how the different symmetries involved in a magnetic structure are changed or are related according to the different symmetry elements that we have. And in general, we want to end up with a set of basis vectors that we use to describe our different types of magnetic structure. So I'd like to explore the basis vector description of magnetic structures. In terms of refinement, well, there are many different philosophies. Many of them start off with some form of take on Landau theory and continuous phase transitions, but these open your door to particular simple approximations, zeroth order approximations that may guide you in particular directions in a kind of hand-waving approach. Couplings can happen, and we'll start to see going on all of the possibilities. In general, I have a building up principle based on Occam's razor and building up based on what you need to do based on the analysis of your data, but always take care of what is unknown. In the later part of the workshop, we're going to be going through using Sarah, and I'll be concentrating on Sarah with foolproof. So let's kick off. Why should an experimentalist use symmetry? And despite rumors, I still count myself as being an experimentalist. So to start off with is we have a magnetic system with some Hamiltonian, but the problem is we don't know what is in that Hamiltonian, and there are many possibilities. I often work with magnetic neutron diffraction data from powders, and we have information that's destroyed in a variety of different ways according to the physics of our samples and the technique that we're using, magnetic form factors, magnetic structure factors. By the time we go through powder averaging and domain averaging, we end up with a problem that's very underdefined if we have to treat all of the possible variables. An example of this would be trying to take a data set here, which was from beta manganese ruthenium, and trying to find a magnetic structure from within that. Some structures are very complicated, so they're not going to lead to simple magnetic structures. So what happens? We can't always simply expect an easy answer. Now, when we're looking at phase transitions in solids, a starting point is often coming from Landau theory and involves symmetry breaking. So we're going to a transition with some lower phase, going from a high symmetry phase to a lower symmetry phase. You can work with Landau theory. An example of this would be going from paramagnetic phase, where we have no net magnetization, to an antiferromagnetic phase, where in this case we have collinear but antiferromagnetic alignment of spins. And when we do this, some symmetry operations are lost. And this is involved in the phase transition. To start off with, we have to start building up our symmetries or understanding our symmetries that we have before we start thinking about magnetism. And that's a space group. The space group is a set of symmetry elements or operations, and then the product of any two elements is a member of the group. That's what we have written here. And we can go through various products, rules of group theory, and we can come up with a set of rules required for a space group. When we apply symmetry operations, such as here, we apply an E in an E operation, we end up with an E, the identity operation. If we apply an E in the C2Z operation, we end up with C2Z, and so on. So this is a multiplication table saying what happens when you apply one symmetry operation and then another symmetry operation. And all of these results must be part of the group. So they're represented here along the row or down the column. So we can take these operations and combine them using mathematics. So here we have a multiplication symbol for some form of matrix describing that symmetry operation, and similarly for the C2Z giving us the solution as a sigma YZ. Irreducible representations are matrices that are combined in the same way that symmetry operations combine, according to the same multiplication tables. These matrices in general can be rewritten into a form where we only involve block diagonals in these matrices, in which case we can deal with these block diagonals separately. So dealing with these small squares separately, and then these larger squares separately. This takes something we call a reducible representation. It represents the symmetry operations and follows the same matrix mathematics, but is broken up into two parts that are irreducible. We can't have any smaller unit than this small block, and we can't divide this larger square into smaller units either. So we have irreducible representations, a set of symmetry operations that combine in a manner that follows the group multiplication tables. In point groups, we can have representations of matrices of order 1, 2, or 3. And we often use notations of A and B for order 1, E for order 2, and T for order 3. In space groups, when we start dealing with rotational translational symmetry operations, these matrices extend from being 3 by 3 ones to being up to order 6. So there's a marked complexity in possible types of symmetry operations and possible types of structures. Now, just as I said that we can start off with this matrix representation, may be reducible, defined according to some matrix set of D, they can be separated into irreducible representations, and there's a decomposition relationship here. So if we have a simple case where we have C3V, here are our symmetry operations, and here are our notations for our different irreducible representations, we can take the reducible representation and work through this equation to calculate the number of times that a particular irreducible representation is contained within a reducible representation. So we're using the character of the matrices here, which is given a symbol chi. Chi G is a character of the matrix of the irreducible representation that we're looking at, and chi G is the character of the matrix of the irreducible representation that we're looking at. And in this particular case, we can see that the number of times A1 is there is 1 time, the number of times A2 is there is 0. If you go through the matrix mathematics of the characters, it will cancel. So A2 is not compatible with this reducible representation. If we look at the matrices, here's an old paper of Bertaut, and you can see what these matrices look like. We have a simple representation going across the symmetry operations, which is all 1, the unity representation. Then we have the second representation, gamma 2, and you've got a set of 1s there and minus 1s there. And similarly for gamma 3, we have 2 by 2 matrices with a variety of forms. Now we have irreducible representations. The challenge we have is to build the compatible magnetic structures, or the magnetic structures that correspond to those irreducible representations. To do this, again, we have to work through the different types of symmetries that we have. We have the propagation vector defining translational symmetry. We start off with a space group, a parent symmetry. We have to work out symmetry operations that are compatible with the propagation vector. Then we have the atomic position, thinking about a magnetic moment of that position, and then whatever else we know about the Hamiltonian. In terms of rephrasing symmetries, here's a set that we're going to be working through. I'm just going to skip over this slide because it's in your notes, but if you go back and look at it, you'll see the different types of symmetries that we've been going over. So in general, for magnetic structures or phonons, or electronic orbitals, we think about them as being a linear combination of plane waves. So we think of them as Fourier components. It comes from Bloch waves being the eigenfunctions of the periodic Hamiltonian, and they can be constructed again from Fourier components. So we think of a magnetic structure as being constructed from basis functions, where we have some basis function here that is translated according to a wave equation, according to exp minus 2 pi I k dot t, t being a translation as you move through the unit cell to this position j here, where we come up with our final basis vector. Basis vectors can be combined according to a weighting coefficient or mixing coefficient to make our overall magnetic structure. So this is our magnetic vector, which is an axial vector. We can start off by defining the moments in the primitive unit cell, and then the K vector will define all of the others in the spin structure. To keep the notation simple, I'm going to drop those arrows that are on top of the vectors to stop the equations being too crowded, but it should be remembered that they are there to be explicit in the vector notation. So the job of the propagation vector is to propagate the magnetic structure through the crystal. If we start here with a spin or magnetic moment that's pointing along the B direction, we have a propagation vector that's 0, 0, a half. So that means every unit translation along the C direction corresponds to a pi reversal in the magnetic moment. We see it flipping in opposite directions. So you can see how this comes to play in k dot t. K is 0, 0, half. So every translation, we go from 0, 0, 0 to 0, 0, 1 to 0, 0, 2. We're translating one unit along the C direction, and that leads to a pi phase shift as we go through our basis functions. The formalism of the propagation vector then enables us to define many types of magnetic structures, where the only thing we actually need to find are the moments in the 0th unit cell, the primitive unit cell, and to use a propagation vector. The next thing that we have to do is we have to take our space group and we have to think what happens when we apply this propagation vector. We need here only to consider the rotational part of the symmetry operation, which in Sykes notation is h, and the translational part is tau. So we're just thinking about the h part, the rotation part. We need the subset of symmetry operations of the space group that leave the propagation variant according to this equation here. K is a vector in reciprocal space, so we think about h, our rotational operation, being in reciprocal space. So it's k multiplied by h rather than h multiplied by k. And this defines those symmetry operations are compatible with the translational symmetry of the problem, which is the propagation vector k. We're looking for symmetry operations h that leave the propagation vector invariant, that turn k into k prime, related by some reciprocal lattice vector. If we take the example of space group 227, k equals 0, we have 48 symmetry operations. This corresponds to the gamma point in the Brillouin zone. If we go to half 0, 0, the k point, we see that there are only 8 symmetry operations that are compatible with that k vector, that leave it unchanged with respect to a reciprocal lattice translation. So we see that the different points, lines, and planes in the Brillouin zone will have different rotational symmetry operations h that leave that propagation vector invariant. There's various notations that exist in the literature, but I'll be using principally that of Kovalev and Kovalev's tables. So when we have, for example, k equals a half, a half, a half, we have 12 symmetry operations that are compatible with that k vector that leave it invariant. But we started with 48. So the question is, what happens to the others? The other symmetry operations rotate that propagation vector into symmetry-related ones. And together, these symmetry-related, these rotationally related propagation vectors form a star. We call this a star of the propagation vector. It's in reciprocal space. And in general, when we're combining basis vectors together to make our spin structure, to make our moment vectors, we can combine basis vectors with different propagation vectors, sometimes from different arms of the same star, sometimes from different stars altogether. Moving back to the space group, so we have our space group, and just as that had all of the rules of group theory defining a group, the same thing happens for GK. symmetry operations that are compatible with the propagation vector k are also a space group. And that's what we have here when we define our irreducible representations. We have the symmetry operations of GK, and we can use these to construct our irreducible representations of the little space group GK. Some books have character tables of irreducible representations, but that's not enough. When you actually want to start making magnetic structures, you need to have actual irreducible representation matrices, and the sources of these are important. So irreducible representations define basic types of symmetry for a group of symmetry operations. Other symmetries can be built from them by combining different irreducible representations. So we can combine different irreducible representations according to some number to make our overall structure symmetry. Again, in molecules, we have point groups, so we go up to 3 by 3 matrices. Here, the matrices go up to order 6. The next step that we have to do is to go from irreducible representations to basis vectors. What are we trying to do? Here we're trying to work out what types of structure, magnetic structure, are possible for moments at atomic positions. There are two things that we need to be thinking of. One, how the atoms are interchanged under the symmetry operations of GK. And this creates what's called the permutation representation. And then how magnetic moments are rotated under the symmetry operations of GK. And this is called the axial vector representation. And we're going to take those overall symmetries and we're going to decompose them, we're going to look at them in terms of the irreducible representations of GK. The permutation representation. So, with a quick recap, crystal structure is invariant under the symmetry operations of its point and space group. But in equivalent positions, symmetry-related positions can be interchanged, or rather, they can be permuted. For example, here we have 3 atoms A, B, and C. We've got 2 symmetry operations that are sigmas, sigma 1 and sigma 2, and we've got a rotation around the threefold axis of the triangle. Sigma 1 is going to turn A into A, B into C, and C into B. You can see that just looking at the picture. The character of the number of atoms are left unchanged. So the character for this symmetry operation is going to be 1. Only A is left unchanged by these symmetry operations. Sigma 2 instead takes A to C, B to B, and C to A. So B is now left unchanged. So the character of sigma 2 is also 1. It just corresponds to a different atom than we had for sigma 1. But the threefold rotation operation turns A to B, B to C, and C to A. So we have no atoms that are left unchanged. So we have the character of the permutation representation for the different symmetry operations coming from this. Next, we have to consider the symmetry of the magnetic moments. These also could be displacement vectors, and we have to consider their symmetries under improper rotations. A simple vector, a polar vector, is inverted when we go through an inversion center. But axial vectors should be considered as having the symmetry of a current loop. So here we have an electronic charge going around, and we have the resulting magnetic field. When you go through an inversion symmetry, if you go from here to here and there to there, then you'll actually see that current loop goes around in the same direction as before. So the magnetic field is not inverted when we have an axial symmetry, a magnetic moment symmetry. We can write this in terms of matrix mathematics. So instead of having a rotation matrix being a 3 by 3 operation that's being applied to our X, Y, and Z moment directions, we also have to multiply that by the determinant of this rotation matrix, this 3 by 3 matrix. And this is -1 when we have an improper rotation or an inversion center. And that leads us to something that has the same symmetry as this axial vector. If we put this all together, we have the magnetic representation. Magnetic representation considers moments that are at particular fields. When we're putting this all together, we have magnetic moments at particular positions. So we have to combine the effect of the symmetry operations on the positions, the permutation representation, and the symmetry operations on the moments. These are separate and we can combine them as a simple direct product. And that gives us our representation for a magnetic moment at that position. So this is our magnetic representation. And we can decompose that into irreducible representations of GK. The number of times a particular irreducible representation appears is given by this equation here, where we've got the reducible representation there and the irreducible representations there. This decomposition depends on the atomic site, so we could have the reduction of the magnetic representation for the 2A site being 1 gamma 1 of order 1 plus 1 gamma 2 of order 1 plus 0 gamma 3 of order 2. And a 6C site could be 2 gamma 1 of order 1, 0 gamma 2 of order 1, and 2 gamma 3 of order 2. When you have zeros here, this means that there is no magnetic structure with this particular symmetry type corresponding to that irreducible representation possible on that crystallographic site, the 2A site, or in this case, gamma 2 for the 6C site. Now that we know which irreducible representations are involved in our possible magnetic structures, we can calculate the directions of the magnetic moments themselves that are compatible with this irreducible representation. And this technique uses wonder projection, which starts from a set of test functions, phi1, phi2, and phi3, which correspond to vectors along different orthogonal directions in the crystal structure. So we have phi here, the different test function. We're looking at 1 to start off with. We rotate that test function. Then we multiply by the determinant of that rotation matrix because we're considering that test function as being an axial vector. Then, if the application of the symmetry operation generates a moment in a different position, we have to bring the magnetic structure back to the original position according to a plane wave equation, which is what we have here. And then we have a phasing operation that's corresponding to the irreducible representation in question. And we can use this to calculate what are called the basis vectors, the different moment orientations that are compatible with the irreducible representations. So these basis vectors define the degrees of freedom for our system in terms of moment components. They follow the symmetry of associated irreducible representations, and we can use them to classify symmetry just as irreducible representations classify symmetry. These are the basis vectors associated with an IR, or you can have an irreducible representation associated with basis vectors. They're just different ways of describing the symmetry. Importantly, when we're running through magnetic structures, this type of symmetry classification does not decrease the number of degrees of freedom that we have. Every moment that we have has 3 components. There are 3 degrees of freedom. If you have n atoms, there will therefore be 3n basis vectors. They'll just be classified and categorized according to symmetry. We combine these basis functions according to the mixing coefficients to make our spin vectors. And in general, we can combine those of different irreducible representations within an irreducible representation or involving different propagation vectors k. The next thing I wanted to go through was just building up some simple types of magnetic structure with basis vectors. Here we have our exponential, our Bloch wave that's defining our basis function propagating through the crystal structure. K is our propagation vector. Tij is the translation vector between our basis function component in the 0th unit cell, our seed position, as it were, and that's generated when we have a magnetic moment position such as that at J. C is our weighting coefficient. The next thing that we're going to do is expand this exponential in terms of a real cosine component and an imaginary sine component, and just see what happens in a variety of different magnetic structures. In terms of the simple structures, we can have our translational properties being defined by k dot t. So we have this phase relationship in the exponential. We're going to work with only a single basis function. So our magnetic structure itself is just being created from this basis function that's being propagated according to a cosine function and an imaginary sine function. Now let's consider the situation where this basis function is real. And the propagation vector is such that this sine component goes to 0. If we have this, what we're left with is just this cosine term. And we see that the magnetic structure in this case is simply a cosine function, which is what this simple propagation structure that we had earlier corresponds to. It's a cosine wave. We could move over to an incommensurate system, and essentially we do nearly the same thing. If we consider this case of the basis vector being real, and now k is such that this imaginary sine component is now non-zero. Well, that would lead us to having a spin vector or a moment vector that's complex. But so we need to make this real. And we do this by adding the component of minus k, because the basis function minus k is related to the basis function k by complex conjugate relationship. So if we add this basis function, we add the complex conjugate. If we substitute these two parts into our expression, we're going to have the magnetic moment as being 2 times the real part of the basis function, cosine minus 2 pi k dot t, plus 2 times the imaginary part of the basis function multiplied by sine minus 2 pi k dot t. Where the second term is 0, so this corresponds to the basis function psi being real, then again we end up with just this real part here, which will be modulated according to a cosine structure. So we have 2 times the real part of the basis function being modulated by a cosine wave. So this creates a spin density wave, often called a sine structure, but really it's actually a cosine structure if you take this particular formalism. If we have a situation of the basis function being complex and k being incommensurate, again, this would lead to the spin vector or moment being complex, and we need to make things real. We do this again by adding the basis function according to minus k. If we work through the mathematics, we now have that leading to 2 times the real part of the basis function cosine minus 2 pi k dot t, and again, plus 2 times the imaginary part of the basis function sine minus 2 pi k dot t. But now this second term is not going to be 0. So we have a cosine propagating component here, and then we have an out of phase sine propagating component with the parts according to the basis function of the real part and the imaginary part not being collinear. So the real part and the imaginary part are not parallel. So this now leads us to a circular elliptical helix. If we have the imaginary part of the basis function being the same magnitude as the real part of the basis function, then we're going to end up with a circular helical structure. If they're different magnitudes, then we'll end up with an elliptical helix. So you're seeing this naturally comes from this propagation vector formalism and using Bloch waves. So in general, we build up magnetic structures from having some basis vectors that we project out, and we propagate them according to the k vector to make the different types of structures. We can have simple structures would be a sine structure where k is incommensurate and psi is real. We can have circular helices where k is incommensurate and now psi is complex with non-collinear real and imaginary components. You can make conical structures by mixing incommensurate k with complex non-collinear components and a separate k equals 0 component. So you're mixing an antiferrometric and ferrometric component perpendicular to each other. So a conical structure is a combined structure. We can make cycloids where k is incommensurate, psi is complex and non-collinear, etc. So we can make lots of different types of structures. What happens? Well, what happens depends on what's going on in your sample, either through exchange interactions, but also through entropy arguments. So in general, you should consider these types of magnetic structures as being simple structures made from this summation of basis functions according to a plane wave equation. And these are like end members that perhaps we need to combine or we need to mix or merge according to that summation that we're having of these different propagating waves.